All right. How's everybody doing today? Welcome to my channel. And this is an educational channel. We look at theories of everything that have inspired me and helped me out with my paradigm shifting, my awakening to 5D consciousness, and my formation of a holistic worldview. Today is our 514th video that we have done on the reciprocal system of theory from Dewey B. Larson. And won't go into it too much, but if you'd like to hear me go into the explanation of the reciprocal system of theory, starting with Larson's two fundamental postulates and his formation of a theoretical universe, you want to watch one of my first 474 videos on this subject, and then maybe come back and catch this video. If you feel like you're okay with being a bit confused, just stay tuned, and we're going to get into chapter 23 of Larson's book on basic properties of matter, the name of the book, and chapter 23 is called Charges in Motion. And here's how it starts off. When a negative asterisk charge is added to an electron, the net total scalar speed of the charged particle is 0. But since the electron rotation has the inward scalar direction, while the charge has the outward direction, the two motions take place in different scalar dimensions. Thus, the electron does not act physically as a particle of 0 speed displacement, but as an uncharged electron and a charge. A moving charged electron therefore has both magnetic properties, those of moving uncharged electrons, and electrostatic properties, those of charges. The conventional view is that electrostatic phenomena are due to charges at rest, and magnetic phenomena are due to charges in motion. But, in fact, charges in motion have exactly the same electrostatic properties as charges at rest. Quote, "It is one of the remarkable properties of electric charge that it is invariant at all speeds," says E.R. Dobbs. So motion of the charges is not in itself sufficient to account for electromagnetism. Some additional process must come into operation in order to enable a charged particle to exhibit magnetic properties when in motion. Whether this additional process involves the charge or the particle, the, quote, carrier of the charge, as it was called in a statement previously quoted, is not specifically indicated observationally. Present-day theory simply assumes that all effects are due to the charges, but since there are carriers, these are obviously the moving entities. The charges have no motion of their own. They are carried. Even on the basis of conventional theory, therefore, the electromagnetic phenomena are due to the motion of the carriers, not motion of the charges. The development of the electromagnetic theory in chapter 21 now verifies this conclusion and identifies the carriers of the charges as, quote, bare electrons. As noted in chapter 13, a flow of charged electrons through a conductor, a time structure, follows the same course as the flow of uncharged electrons. But the charged electrons have a property that their uncharged counterparts do not have. They can also move freely through the gravitational fields of extension space, producing electromagnetic phenomena that correspond to the effects of the flow of current in conductors. This is illustrated by an arrangement such as that shown in figure 25. In the center of the diagram is a wire through which a current is moving downward, as indicated by the arrow. The conventional, quote, direction of current flow, end quote, is opposite to the actual movement of the electrons and is upward. At the right is another conducting wire so arranged that a segment of the wire is hanging loose in a container filled with mercury. When a current is passed through this system in the same downward direction, the loose end of the wire is attracted toward the center wire. At the left of the diagram is a vacuum through which a stream of electrons is also moving downward. This stream is attracted toward the center wire in the same way as the loose wire in the mercury container. The movement of charged electrons through extension space is quite different in some other respects from the movement of uncharged electrons, or space units, through matter. For instance, no electrical resistance is involved, and the motion therefore does not conform to Ohm's law. But the magnetic effect depends only on the neutralization of one dimension of a quantity of gravitational motion by the translational motion of the electrons. And from this standpoint, the collateral properties of the motion are irrelevant. As long as the motion of the charged electrons takes place in a gravitational field, the requirement for the production of magnetic effects is met. On the basis of the general principles applying to electromagnetic forces defined in Chapter 21, the magnetic force on a charged particle in a magnetic field is the product of the magnetic field intensity, B, and a motion combination with the dimensions s squared over t. The combination applicable to the motion of a charged particle, we find, is electric quantity Q, measured as charge, lowercase q, multiplied by the particle velocity v. The force separation is then F equals B lowercase q v, with spacetime dimensions t over s squared equals t over s to the fourth times s over t. The I think it's t squared over s fourth. The static force of the charge is F equals lowercase qe, and the dimensions of which are t over s squared equals s times t over s to the third. The electrostatic forces between the charges, units of capital Q, are independent of the magnetic forces due to the movements of electrons, units of lowercase q. The total force acting on a charged electron in a magnetic field is then F equals capital QE plus B lowercase qv. Since uppercase q and lowercase q are numerically equal because each electron takes 1 unit of charge, this force expression can be written F equals lowercase q, the quantity E plus BV. The combined force is known as the Lorentz force. Lorraine and Carson comment on this force as follows, quote, the Lorentz force of this equation is intriguing. Why should V times B, velocity times magnetic field intensity, have the same effect as the electric field E? Clearly from this equation, the particle cannot tell whether it sees an E or a V times B term. Thus, V times B is somehow an electric field intensity, end quote. The authors then go on to say that the explanation is provided by the theory of relativity. But the space-time analysis shows that relativity has no bearing on this situation. From a physical standpoint, electric field intensity acts on a charged particle not as field intensity, but as a quantity of T over S3. Similarly, magnetic field intensity, T squared over S to the fourth, acting against an electron moving with a velocity S over T, has the effect of a quantity of T squared over S to the fourth times S over T. That is a quantity of T over S third. The magnitude of the physical result is the same in both cases. Excuse me. This is not an unusual situation. On the contrary, it is common throughout all kinds of physical phenomena. The increase in temperature due to the addition of energy, for instance, depends entirely on the quantity of T over S that is added to the thermal motion. It is immaterial whether that energy increment is in the form of kinetic energy, chemical energy, electrical energy, or any other form of T over S. The effect of V times B does differ from that of E in direction, and the expression given for the Lorentz force is therefore valid only in vectorial form. The electric force QE acts in the direction of the field, and because the field is radial, the charges to which the force is applied, quote, are accelerated, gaining kinetic energy, end quote. The effect of the magnetic forces follows a different pattern. For the reasons explained in Chapter 21, the force exerted by a magnetic field on a moving electron is perpendicular to the field. As noted in the discussion of electromagnetism, this perpendicular direction of the force is an unexplained anomaly in present-day physical thought. Quote, the strangest aspect of the magnetic force on a moving charge is the direction of the force, says a current textbook. When the origin of the magnetic field is understood, there is nothing strange about this direction. The scalar dimension of the motion of the electron is the dimension in which a portion of the gravitational motion is neutralized by the one-dimensional electron movement, and the residual two-dimensional electron necessarily exists in two perpendicular dimensions. The force aspect of this residual motion is also perpendicular to the magnetic field. If this is a magnetostatic field, it has the outward scalar direction, whereas the residual force has the inward scalar direction and must therefore be in a different scalar dimension. If the field is electromagnetic, the forces are likewise in different dimensions, although the cause is different. As noted earlier, the motion of the uncharged electrons that constitute the electric current is in a scalar dimension other than that of the reference system. A freely moving charged particle, on the other hand, is moving in the space and therefore in the scalar dimension of the reference system. The acceleration of an electron moving in a uniform magnetic field is thus perpendicular both to the field and to the direction of motion. Such an acceleration does not change the magnitude of the velocity, it merely changes the direction. Motion at constant speed with a constant acceleration at right angles to the velocity vector is motion in a circle. If the particle is also moving in a direction perpendicular to the plane of the circle, the motion path is a spiral. Most of the empirical knowledge that has been gained with respect to the nature and properties of subatomic particles and cosmic atoms has been derived from observations of their motion in electric and magnetic fields. Unfortunately, the amount of information that can be obtained in this manner is very limited. A particularly significant point is that the experiments that can be made on electrons by the application of electric and magnetic forces are of no assistance to the physicists in their efforts to confirm one of their most cherished assumptions, the assumption that the electron is one of the basic constituents of matter. On the contrary, as pointed out in Chapter 18, the experimental evidence from this source shows that the assumed nuclear structure of the atom of matter, which incorporates the electron, is physically impossible. The theory postulating orbital motion of negatively charged electrons around a hypothetical positively charged nucleus, developed by Rutherford and his associates after their celebrated experiments with alpha particles, collided immediately with one of the properties of the charged electrons. A charged object radiates if it is accelerated. Since the charge itself is an accelerated motion for geometrical reasons, the force required to produce a given acceleration of the charge is less than that required to produce the same acceleration of the rotational unit. But the charge is physically associated with the rotational combination and must maintain the same speed. The excess energy is therefore radiated away. This loss of energy from the hypothetical orbiting electrons would cause them to spiral in toward the hypothetical nucleus and would make a stable atomic structure impossible. This obstacle in the way of the nuclear hypothesis was never overcome. In order to establish the hypothetical structure as physically possible, it would be necessary to, 1, to determine just why an accelerated particle radiates, and 2, to explain why this process does not operate under the conditions specified in the hypothesis. Neither of these requirements has ever been met. Bohr simply assumed that the motion of the electrons is quantized and can take only certain values, thus setting the stage for all of the subsequent flights of fancy discussed in Chapter 18. The question as to whether the quantum assumption could be reconciled with the reasons for the emission of radiation by accelerated charges was simply ignored, or was the even more serious problem of accounting for the assumed coexistence of positive asterisk and negative asterisk charges at separations much less than those at which such charges are known to destroy each other. It should be no surprise that Heisenberg eventually had to conclude that the nuclear atom he helped to develop is not a physical particle at all, but is merely a symbol, that is, a mathematical convenience. All of the foregoing discussion of the phenomena involving charges in motion has been carried out in terms of charged electrons. The same considerations apply, inversely in some respects, to charged positrons. Like the charged electrons, these positively charged particles are capable of moving through space, and since their motion is outward, differing from that of the charged electrons only in rotational speed, they produce the same kind of magnetic effect as the charged electrons. In the cosmic sector, the cosmic electric current is a flow of uncharged positrons through cosmic matter. Charged positrons moving through the cosmic gravitational fields in time have magnetic properties. The rotational vibration that constitutes a charge may also be applied to other particles or to atoms. The charge of an atom or multi-unit particle and the unit of rotation that it modifies constitute a semi-independent component of that entity. The combination of charge and rotational unit remains as a constituent of the atom or particle, but vibrates independently in the same manner as the magnetic motion combinations discussed in Chapter 19. Inasmuch as this vibrating combination has the same composition as a charged electron or positron, a unit rotation modified by a unit rotational vibration, it has the same electric and magnetic properties. The charges on atoms may be either positive asterisk or negative asterisk. As explained in chapter 17, however, negative asterisk ionization is confined to a relatively small number of elements because an atom must have a negative rotation in order to acquire a negative asterisk charge. And effective negative electric rotations are confined almost entirely to the elements of division 4. On the other hand, any element can take a positive asterisk charge. If the rotation in the electric dimension of the atom is negative, so that the positive asterisk charge cannot be applied in this dimension, it can be applied to the rotation in one of the magnetic dimensions. The magnetic rotation is always positive in the material sector. It follows that while the mobile subatomic particles are predominantly negative asterisk, that is, electrons, the freely moving gaseous ions are predominantly positive asterisk. The charged particles with which we have been concerned in the foregoing pages are electrically charged. Since there are also particles that are capable of taking magnetic charges, the question arises, why do we not observe magnetically charged particles? The explanation can be found in the requirement that the net rotational displacement of a material atom or particle must be positive. The magnetic displacement, which is the larger component of the total, must therefore also be positive. This means that only negative magnetic charges can be applied to material particles. The particles with magnetic rotational displacement are the neutron and the neutrino. The neutron has no electric displacement and only a single unit of magnetic displacement. Addition of an oppositely directed unit of charge therefore reduces the net displacement to zero and terminates the existence of the particle. The neutrino has both electric and magnetic rotational components and can therefore take a magnetic charge, but when it is in this charged condition, it cannot move through space for reasons that will be explained in chapter 24, where the role of the charged neutrino in physical processes will be examined in detail. This chapter concludes the discussion of magnetism as far as this subject will be covered in the present volume. Before turning to a different subject, it will be appropriate to make a few comments on the contents of the last 5 chapters and their relation to the physical situation in general. Because of the theory of the universe of motion, the detailed development of which is being described in these volumes, is new to the scientific community and conflicts with many ideas and beliefs of long standing, the presentation in the several volumes of this series has a twofold objective. It is designed not only to report the findings of the investigation based on the new theory, but also to provide the evidence that is required in order to confirm the validity of the findings. It therefore needs to be emphasized that the points brought out in the discussion of magnetism in these 5 chapters have made a very significant contribution to the mass of confirmatory evidence that is now available. The particular importance of the magnetic evidence lies in the fact that the theory defines a specific dimensional relation between electricity and magnetism. It follows that whenever the theory identifies the nature of an electric phenomenon, this identification carries with it the assertion that there also exists a corresponding magnetic phenomenon, differing only in that it is 2-dimensional, while the atomic analog is 1-dimensional. Thus, we find from the theory that there is a 1-dimensional rotational vibration identified as an electric charge, which has the space-time dimensions T over S and gives rise to a variety of electrostatic phenomena. According to the theory, it necessarily follows that there must be a two-dimensional rotational vibration, a magnetic charge, with the dimensions t squared over s squared that gives rise to an analogous variety of magnetostatic phenomena. The observations verify the existence of a class of phenomena of this type, and an analysis of the dimensions of the magnetostatic quantities shows that they are, in fact, related to the corresponding electric quantities by the factor T over S, as required by the theory. The dimensional interaction between electricity and magnetism is a particularly significant demonstration of the predictive power of the theory. We find from theory that gravitation is a three-dimensional scalar motion, and that an electric current is a one-dimensional flow of units with the dimensions of space through the three-dimensional gravitating objects. From this, it follows that the interaction should have a two-dimensional scalar residue oriented perpendicular to the current flow. Observations show that such a residue does exist, and that the process which leads to its existence can be identified with the phenomenon known as electromagnetism. It further follows from the same premises that the equivalent of a two-dimensional scalar motion through a three-dimensional gravitating object leaves a one-dimensional scalar motion as a residue. This interaction can be identified with the observed process known as electromagnetic induction, and the residue can be identified as an electric current. The principal dimensional consequences that can be inferred from the theoretical identification of the electric current, electromagnetism, and gravitation with 1, 2, and 3 dimensions of scalar motion, respectively, are thus definitely correlated with observed electric and magnetic phenomena. But this is only the groundwork of a massive accumulation of evidence confirming the dimensional relations derived from theory. Contemporary science places a great deal of emphasis on the predictive power of new theories. This is probably an overemphasis, as the ability of a theory to correlate existing information is as important as its ability to point the way to new information, and is becoming increasingly important as, quote, the multitude of different parts and pieces that now constitutes physical theory continues to expand. In any event, it should be recognized that the deductions from the premises of a theory that identify hitherto unknown relations among known phenomena are predictions in the same sense as asserting the evidence of a hitherto unknown phenomenon. For example, the postulate that motion is the sole constituent of the physical universe carries with it the consequence that all physical quantities can be expressed in terms of space and time only. This is a prediction. The assertions as to the relation between electric and magnetic quantities discussed in the foregoing paragraphs are likewise predictions based on the same premises. The fact that the development of the consequences of the postulates of the theory of the universe of motion in the pages of this and the preceding volume has led to a complete and consistent system of space-time dimensions applicable to mechanical, electrical, and magnetic quantities is a verification of those predictions. The verification of this prediction is all the more significant because the possibility of arriving at any consistent system of dimensions, even with the use of 4 or 5 basic quantities, is denied by the majority of physicists. In the past, the subject of dimensions has been quite controversial. For years, unsuccessful attempts were made to find ultimate rational quantities in terms of which to express all dimensional formulas. It is now universally agreed that there is no one absolute set of dimensional formulas. A similar prediction concerning the numerical values of these physical quantities is also implicit in the postulates. Since it is postulated that motion exists only in discrete units, it follows that the other physical quantities, all of which are either motions, combinations of motions, or relations between motions, likewise exist only in discrete units related to the units of the basic motion. This means that when the physical relations are correctly stated, they contain no numerical errors other than those specifically identifying numbers of units, such as the atomic number, for example, the so-called fundamental constants of physics, and the multitude of disposable constants that appear in relations such as the equations of state will all be eliminated. This fact that the values of the fundamental constants have no physical meaning in the context of the theory of the universe of motion contrasts sharply with the place of these constants in current scientific thought, where they are regarded as critical magnitudes that determine the nature of the universe. Paul Davies expresses the prevailing view in this statement. Quote, the gross structure of many of the familiar systems observed in nature is determined by a relatively small number of universal constants. Had these constants taken different numerical values from those observed, then these systems would differ correspondingly in their structure. What is especially interesting is that in many cases, only a modest alteration of values would result in a drastic restructuring of the system concerned, end quote. As we have seen in the pages of this and the preceding volume, some of these constants, the speed of light, the electron charge, etc., are natural units. That is, their true magnitude is unity, and the others are combinations of these basic units. The values that they take in the conventional measurement systems are entirely due to the arbitrary magnitudes of the units in which the measurements are expressed. The only way in which the constants could take the different numerical values to which Davies refers is by modification of the measurement system. Such a change would have no physical meaning. Thus, the possibility that he suggests in the quoted statement and explores at length in the pages of his book, The Accidental Universe, is ruled out by the unitary character of the universe. No physical relation in that universe is accidental. The existence of each relation of the relevant magnitudes are necessary consequences of the basic factors that define the universe as a whole, and there is no latitude for individual modification, except to the extent that selection among possible outcomes of physical events may be determined by probability considerations. Okay, we will finish this chapter tomorrow and head on to the next chapter. Thanks for tuning in today, and have